Just look at this. I mean, what an incredible amount of water, all being held back by a concrete wall. But what's really happening here? There's this invisible force at work, a force that actually gets stronger and stronger the deeper you go. So what is it?
Okay, so today we're diving into exactly that. We're going to break down that invisible force, pressure. And, it's literally everywhere, from the air you're breathing right now to the deepest parts of the ocean. And understanding it is absolutely key to understanding how our world actually works.
So here's how we're going to break it down. We'll start with the force that's pushing on you right now. Then we'll define what pressure really is. After that, we'll dive into how it works in fluids, clear up a few key terms like absolute versus gauge, and finally, we'll look at why it all matters so much. Let's jump right into our first section, the invisible force. It sounds kind of mysterious, doesn't it? But you're actually experiencing it this very second. I want you to think about it like this. You are standing at the bottom of a giant ocean, an ocean of air. All of the air above you, stretching for miles up into space, actually has weight. And gravity is constantly pulling that huge column of air down. And that weight pushing on you is what we call atmospheric pressure. So that brings us to part 2, pressure, the basic idea. Because look, we know there's a force, but the effect of that force completely depends on how it's applied. It's all about how you push. So here it is, the core idea. Pressure equals force divided by area. In other words, it's the amount of force you're putting on a surface spread out over a specific area. The key thing to remember is that it's not just about how hard you push, but how concentrated that push is. And the official unit we use to measure it is the Pascal. And this is the perfect way to visualize that. Imagine someone is standing on your foot. Now, if they're wearing a snowshoe, their weight, the force, is spread out over a really big area. It's no big deal. But what if they're wearing a stiletto heel? Whoa! Now that same exact force, that same weight, is focused on one tiny point, creating enormous pressure. Ouch! Same force, completely different pressure. Okay, so that brings us to part 3, hydrostatic pressure. And now we can finally get back to that dam we saw at the start by talking about how pressure works in fluids, like water. Let's think about 2 total extremes. You've got a deep-sea diver who needs this incredibly reinforced suit just to survive the crushing force way down in the ocean. Then you've got a climber at the very peak of Mount Everest who's struggling to breathe because the air and the pressure is so thin. How can both of these things be happening? It's all because of something called hydrostatic pressure. This is just the pressure inside a fluid that isn't moving. And it works exactly like the atmosphere did. It's caused by the weight of the fluid column sitting right on top of you. The deeper you go, the more fluid is above you, and the greater the pressure becomes. And what's so cool is that this principle works everywhere. It doesn't matter if it's a massive dam holding back a lake or just some water in a container. The pressure at the top is low, and it increases in a straight line the deeper you go. That force pushes outwards, which is exactly why dams have to be so much thicker at the bottom than they are at the top. And of course, we can calculate this. The formula is P equals rho GH. So P is our pressure. That funky-looking P is a Greek letter, rho, and it just stands for the fluid's density, basically how much stuff is packed into it. G is the pull of gravity, and H is for the height or depth of the fluid. So it's pretty simple. More density or more depth equals more pressure. All right, time for part 4, absolute versus gauge pressure. I know this might sound a little technical, but really it's just about your starting point. It's all a matter of perspective. So let me ask you this. When you go to check your car tires and the gauge says 32 psi, that's pounds per square inch, is that the total pressure inside the tire? Well, the answer is no. And understanding why is pretty important. This diagram explains it perfectly. Let's start at the very bottom. Absolute zero pressure. That's a perfect vacuum. Any pressure that's measured starting from this true 0 point is called absolute pressure. But, we don't live in a vacuum. We live up here at atmospheric pressure. The gauges we use, like for our tires, are actually set to treat that as their starting point. So they only measure the pressure above the atmosphere. And that's what we call gauge pressure. So to put it simply, we've got 3 key reference points. Absolute pressure, which starts from a perfect vacuum, atmospheric pressure, which is just the air around us, and then gauge pressure, which measures the pressure above atmospheric pressure. That's why your 32 psi tire is really holding 32 psi on top of all the atmospheric pressure already pushing on it. Which brings us to our final section, the payoff, the power of pressure. This is where we see how all these concepts come together in the real world. We've thrown a few units around, so let's quickly recap where you'll see them. Pascals, that's mostly for scientists. The bar, which is roughly 1 atmosphere, is what you'll hear in weather reports or in scuba diving. PSI, pounds per square inch, that's what you use for your car tires. And that strange one, millimeters of mercury, that's what doctors use to measure your blood pressure.
So why does all this matter? Well, because understanding pressure lets us do some incredible things. We can engineer submarines to explore the deep ocean, use hydraulics to lift a heavy car with a simple push of a pedal, keep our food fresh by using vacuum sealing, and even predict the weather based on tiny changes in atmospheric pressure.
And this is the fundamental rule that makes it all work. Pressure in a fluid that's just sitting there doesn't just push down, it pushes equally in all directions and always straight on, perpendicular to any surface it touches. That's why it can hold up a dam or crush a submarine from all sides at once. So, as you can see, pressure is a truly fundamental force. It shapes everything from the weather in our skies to the engineering that supports our entire way of life. It's a powerful reminder of all the invisible forces that govern our world. And it really makes you wonder, doesn't it? What other hidden forces are out there, just waiting to be understood?